So thanks for the introduction. Yeah, so this is a joint work with Yang and Yingkai from Yale. And so let's start with the very classic revenue optimal auction setting, where we have exactly one item to sell, and there are n potential buyers. And for each buyer I, he has a private value VI, which is drawn from some distribution DI. And our goal is to maximize the revenue. And we know that in this case, Meyerson provides the revenue optimal auction in this setting. And I think everyone here must be very familiar with this result. And we just noticed that one key assumption in this setting is that for each buyer, he knows exactly his value. But however, this assumption can be not realistic or like even impossible in some scenarios. We can have a look at one example here. Suppose a seller is selling a facial cleanser, and there's, for example, a potential buyer I. And for buyer I, he knows that his value VI is uniformly drawn from 0 to 2. But however, he never uses this product. He never uses this product before, so he has no idea that whether this face wash is suitable for his skin. So he does not know his value of this item. So what should we do now? A possible solution is to run an experiment instead. So an experiment here means that the seller can send them like a free trial version of this face wash to the buyer, and the buyer can like have a trial of this item for a few days. And after trying this item, the buyer will receive a signal. But since this is only a free trial, so the buyer can only have a very coarse estimation that's whether this product is suitable for him or not. So, for example, maybe he will get a signal high if the value of this item for him is at least 1, and otherwise, he will get a signal low, which may mean that okay, this item does not match my skin well. And when he receives a signal high, he knows that okay, now my value is uniformly drawn from 1 to 2, and in this case, my belief is 1.5. And suppose he receives a signal low, and he knows that okay, now in this case, my value is uniformly drawn from 0 to 1, and his belief is updated to 0.5 in this case. Okay. And actually, we can formulate this process with an information structure. So what is an information structure here? So it is a pair of Si and sigma I for each buyer. So what is Si? It is the set of possible signals that the buyer may receive. So in this example, it is H or L, high or low. And sigma I is a mapping from values to signals, which may mean that what's the result of the experiment given that his value is VI. And again, so in this example, the mapping maps 0 to 1 to low and 1 to 2 to high. Okay, and the most important thing is that for each buyer, he cannot directly observe his value VI, but instead, he observed the signal, like in this case, is high or low, and and he can only observe this signal. And after that, they will update their belief according to like Bayesian rule. And just a reminder that the signal here is a private information, and only the buyer knows the signal. Like for example, in this case, so after the free trial, only the buyer knows that whether this product is suitable for him or not. And for our work, we consider the joint design problem of information structure and auction. So especially, we assume that the seller can decide both the information structure for each buyer and also the final auction to run. And the goal is to maximize the revenue. And actually, this setting was first considered by Bergman and Tenstover in 2007. Okay. And we can have a look at one example here. Suppose we have two ID buyers whose value are drawn from 0 to 2 uniformly. And the possible information structure for the first buyer can be like this. So this is exactly the same as the example we just had before. And for the second buyer, possible information structure could be like this. So we just tell him nothing. So no matter what his value is, we always send him like a question mark. So in this case, the second buyer has no idea of what his value is. So his belief now is 1. And a possible option could be like, we first ask the first buyer, will you accept the price of 1.5? And if he rejects, we continue to ask the second buyer, will you accept a price of 1? Okay. And in this case, we know that the first buyer will accept this price if and only if he receives a signal high. So in this case, his belief is 1.5, which is exactly the same as the price. And so his contribution of revenue is half of 1.5. And for the second buyer, we know that he will always accept the price of 1. So he will buy this item if and only if the first buyer rejects the price. So his contribution is half of 1. And so the total revenue is 1.25. And actually, this turns out to be optimal in this instance. And just notice that in this case, the distributions of these two buyers are symmetric, but the optimal information structure are asymmetric. Okay, we just have a look at one example, and let's look to the problem itself. So, do we know any structure of the optimal solution in this setting? So one quick observation is that suppose we fix any information structure, then the optimal option should just be the minus option over the induced distributions. So what are the induced distributions? So we still look back to the example before. So for the example we just have, the induced, we notice that with half probability, his belief will be updated to 0.5, and with another half of probability, his belief will be updated to 1.5. So like his induced distribution is just like a half-half. And another quick observation is that suppose we fix the option to wrong, then finding the optimal information structure is just a Bayesian persuasion problem. And I think this is well studied before. So therefore, if we fix any of them, the problem is somehow easy to solve. But what about this joint problem? So,
so why is the standard information design problem? Because you have multiple bidders. So it's more like information design in games, right? It's not just like computation. It's more subtle than that. Because you have multiple bidders.
Yeah.
And their PDs and hierarchy beats also matter, right?
Yeah.
So it's not just commanding against scale.
Yeah, I think so. Okay. Yeah, and in the same paper, they give a characterization of the optimal solution, and they show that there is a finite number of signals in the optimal information structure, and it must be partitional. And moreover, the induced distributions must be regular. So what does partitional mean here? Now suppose this is your distribution. Partitional information structure just looks like this. So it just maps different intervals in your distribution to different signals, and for each signal, it corresponds to an interval in the support. And for each signal, the meaning is like this. It tells you like your value vi falls into this range. Okay. This is a very nice result. It is a very clean categorization. However, suppose now I am the seller and I'm given a particular instance and I am asked to solve this problem. This theorem, it gives a categorization, but it actually does not tell me how to find the optimal solution. Therefore, for our work, we consider the problem of like how to compute this joint design problem and what is the computational complexity of this joint design problem. For our result, we first show that, okay, this joint design problem is NP-hard. So this is kind of negative result. But we have two other positive results. So the first one is that we have a simple partitional information structure with two signals and also together with a sequential positive price mechanism so that its revenue is at least 1 minus 1 over E fraction of the optimal welfare. And our second positive result is a p-task for computing this joint design problem. Okay, and let me first show you the proof of the second theorem. It's quite simple. So let me just remind you the statement here. And just a reminder, so here, the benchmark is the optimal welfare, and we are comparing the revenue with the welfare. And this is impossible in the classic setting. Okay, so as the benchmark is the welfare, we can write it in this one. And so first, what's the simple information structure we use? So we first define Qi to be the probability that I has the highest value among all buyers. So here we use a fixed tie-breaking rule. So there's always only one maximum. So just as a sanity check, this Qi is out to exactly 1. And for our information structure, we just for each buyer I, we send him a signal high.
So like the option you are thinking about is like a revenue maximizing option, right? But here like the welfare is defined for the like total welfare.
Yeah.
But like the option is like minus the revenue maximizing.
Okay. Yeah, basically, but for this one, it's not minus. So for the second theorem, we are not running minus. Yeah. Okay. Yeah. And we will send him the signal high if and only if his value is among the top quantile. And what's the mechanism we run? So we first define BI to be the expected value conditioning on buyer I receives the signal high. And as I said, we are running a special positive price mechanism so that it's asked each buyer whether they will accept the price BI or not. And the order we ask them is according to a descending order on BI. Okay. And so first we can relax. We can use a standard ex-ante relaxation to optimal. So we just need to approximate sigma BI/QI. And for the revenue of our option, we first notice that the utility of each buyer is always 0, since he will accept the price if and only if his value is 1. He receives a signal high, and in this case, his utility is always 0. So as the utility is 0, the revenue is always equal to the welfare. And we only need to show that welfare is a 1 minus 1 over E approximation to OPT, and this is a standard application of correlation gap. Okay, so this is the proof of our second theorem. And for a very high level idea of how our third theorem works, so it's basically a two-step dynamic programming. So in the first part, we basically figure out what distributions of virtual value are inducible by some information structure. So we first figure out that for each buyer I, what kind of virtual value distributions are inducible. And for the second part, we first notice that so it's the revenue of merit option is definitely the expected maximum of the virtual values, and it's just equivalent to like picking an inducible distribution from each buyer, so that the expected value of the maximum virtual value is maximized. And this can be done via step-by-step dynamic programming. And we just need to keep track of the distribution of the maximum virtual value. Okay, so to wrap up, we consider the joint design problem of information structure and auction. And we show that it's NPR, but we have a p-task. And we show that the optimal revenue is at least 1 minus 1 over E fraction of the optimal revenue. So this is a simple correlate, and this is our second theorem. And also, this is almost the end of this talk, but I still want to motivate our setting again. So why do we consider this joint design problem, and why do we allow the seller to have the extra power of information design? So I would say that I have another motivation is that our setting can be viewed as a beyond worst case analysis. So why do I say that? We know that in classic auction, even if there is one item and one buyer, the optimal revenue cannot be comparable with the optimal welfare. But however, I think this is not realistic. Like, suppose you are selling a facial cleanser, and I'm the seller, I get $1, and the customer gets like $1 million, he gets $1 million utility. I think this just sounds crazy. So why does this happen? So we know that some distributions that do not have good revenue guarantee, they just do not appear in practice. And how to explain this? So for our explanation, our explanation is that in the scenarios that the seller can decide how the buyer acquires his information, or the seller can decide how to make advertisement. So in scenario like this, the seller, he has the extra power of information design to rule out these bad distributions. Okay, I think so. This is another motivation. And for functional directions, I'm mainly I'm super interested in like joint design problem in like different settings, since we only consider a very specific setting. So we can have we can consider this joint design problem with many other settings. And I think that's it. Thanks for listening.